4.2, the greatest common factor in equivalent fractions. A common factor is a natural number. Now remember, the natural numbers are all the whole numbers except for 0. So 1, 2, 3, 4, 5, 6, and so on, the counting numbers. It's a natural number that is a factor of 2 or more natural numbers. Now the greatest common factor, which I've got listed here, or the GCF, that's just the abbreviation, is a very special type of a common factor, and we use it when we're writing equivalent fractions. That's how the two ideas are kind of tied in together. So what we're going to do is we're going to practice finding the GCF, or the greatest common factor, and I'm going to show you 2 different ways that you can do it. Now if the numbers are small enough, you can probably do this in your head. But if the numbers are a little bit bigger, then one of these 2 methods might be superior. What I'm going to do is I'm going to take the number 18 and I'm going to write down all the multiples that I can think of 18. Or all the factors that I can think of 18. My factors of 18 would be 1, because 1 divides into 18, 2 divides into 18, and I just kind of run through the list, kind of in my head. The number is small, and I can list them out that way, and I can have 3, and then I can have 6. Now, since these 2 pair up, I'm going to have pairs here and here, so 2 times 9 and 1 times 18. If I take the number 24 now, 1, 2, 3, 4, 6. Now 4 and 6 pair up to give me 24, so 3 and 8, 2 and 12, and of course 1 and 24. The number 42, you can see the bigger they get, they can be more challenging. What goes into 42? Well, 1 does. 1 always goes in. 2, because it's even. 3. 4, no. 5, no. 6 is good. 6 times 7 is 42, so these pair up. So 3 times 14, 2 times 21, and of course 1 times 42. And I've listed all the factors of the 3 numbers. Now I look to see where they have in common. I see they have 1 in common. I see they have 2 in common. I see they have 3 in common. These are all common factors. Common factors, a factor of 2 or more natural numbers, right? 4 is in this one, but not in the others. However, notice here the 6 is in all 3 of them, and that's my last one. I don't have any other factors greater than 6 that are common to all 3. So that's my GCF. My GCF is indeed 6. It's the largest factor of all 3. Now, that's one way to do it. Another way is a little bit more complicated. If you haven't done a factor tree in a while anyway, this is 2 times 9. 18 is 2 times 9. Of course, 9 is 3 times 3. So 18 can be thought of as 2 times 3 times 3, or 3 squared. Then I do the same thing with 24. I break it apart. 24 would be 3 times 8. 8 is 2 times 4, and 4 is 2 times 2. So I'm looking at 24 being 1, 2, 3 factors of 2, and 1 factor of 3. 42, that's 6 times 7, and 6, of course, is 2 times 3. Those are my primes there. So 42 is equal to 2 times 3 times 7. These are the prime factorizations of 18, 24, and 42. Now I look and I see that they have 2's in common and they have 3's in common. This one's got a 7, but the others don't. So 2 and 3 are the only ones that I'm worried about. So I look at the 2's to see how many they have in common. Not total, but in common. This one has 1, this one has 3, this one has 1. They all have at least 1. 3, this one has 2, this one has 1, this one has 1. They all have at least 1. Of course, 2 to the first is 2, and 3 to the first is 3. So this is just 2 times 3, which is 6. And I got the same answer that I did the first time. So you can kind of look at it. And as I said, if the numbers are small enough, you can probably do a lot of this work in your head by running through factors that go into both. That's what I'm going to do on these problems down here. Find the GCF of 12 and 30. So I'm thinking of my multiples, I think of my times tables, and I'm thinking of 6. 6 times 2 is 12, and 6 times 5 is 30. It's the largest number that goes into both. Now, if that isn't something that just snaps right into your head, then try one of these 2 methods. Here, they're 22 and 55. They both have the same digit twice. That makes me think of 11. 11 goes into that. 11 goes into that. That is the largest number that is a factor to both. That's my GCF. Now, the next one, I have 3 numbers, like my first example, and so I have to look at 27, 45, and 90. Now, when the numbers get bigger, it might be easier to go through these steps. It might take a while longer, but that way you can be sure that you're getting the correct answer. But I'm looking at these, and I'm thinking 9. 9 times 3 is 27, 9 times 5 is 45, 9 times 10 is 90, and that's my GCF. Now, this one seems almost like a contradiction. Numbers that divide into 9 don't divide into 14 and vice versa, except for the number 1. That's my GCF. When the GCF is 1, then the numbers are said to be, and that's these guys right here, are said to be relatively prime. Relatively prime. Two numbers are relatively prime if their GCF is 1. Now let's consider this with monomials. Remember, monomials from a previous section we discussed were either numbers, variables, or the product of a number and one or more variables. And that's what I have here. I have some expressions with variables. These are monomials. The number part, remember, is called the coefficient, and that's the variable. This is the coefficient, that's the variable. So what I'm going to do is I'm going to break it into two parts. I'm going to find the GCF of the coefficients, the numbers. 6 and 15, the GCF would be 3. 3 is the largest number that goes into both. And then I look at the variables. I see that they both have one factor of x. So x is common to both. Now, because they only have a single factor of x, I don't combine them, I don't add them. I have one factor of x that's common to both, so one factor of x in my GCF. My GCF there is 3x. On the next example, the coefficients are 20 and 36. The largest number that I can think of that divides evenly into 20 and the 36 would be 4. So 4 goes into both of those, and then I notice that they have variables. They have the variable x. So I'm going to put the x down. They both have an x. This one has 2 factors, however, and this one only has 1. So they have 1 in common. They each have at least 1x. So again, just one factor of x there. 4x is my GCF. On the last example, I threw a couple variables in there. 27 and 39 are my coefficients. The biggest number I can think of that goes into both of those would be the number 3. So I'm going to start off with a 3. Now, if you're not sure that it's 3, you go through the steps that I showed you before by finding the GCF of the numbers, of the coefficients. And then they have variables in common. They both have variable m. They both have the variable, they both have the variable m. Excuse me. This one is the variable n, and this one is the variable p. So, because they only have m's in common, I'm only going to put the m down, and notice that I have 3 factors of m in the first one. I have 2 factors of m in the second one. Right? You see that? So 2 is the lesser of the 2. That's what they both have in common. They both have at least 2 factors of m. So 3m squared would be my GCF. You can have a GCF that has more variables, but we only had, in that last example, we only had the one variable that was common to both monomials there. Now, equivalent fractions, you've done this before. You've done this way back in grade school. This is just a quick refresher, are 2 fractions that represent the same number. Any fraction has an infinite number of equivalent fractions, because what you can do to write equivalent fractions is you can multiply top and bottom by the same non-zero number, or you can divide top and bottom by the same non-zero number. So if I multiply top and bottom by 2, then by 3, then by 4, then by 5, then by 6, and so on, I could get as many equivalent fractions as I wanted to. We want to make sure that we also know that we can divide top and bottom by something maybe that they have in common, by GCF, for example. Now, if I look at my first example, my only example right here, it says write 2 fractions that are equivalent to 12 over 8. Now, what I'm thinking is if I do the top and multiply top and bottom, let's say by 2, I would have 2 times the top, 2 times the bottom. That would be 24 over 36, and that would be indeed an equivalent fraction. It looks different than 12 over 18, but it has the same value. Also now, if I was to divide top and bottom by a number, now I might divide by 2 or by 3 or by 6. I doubt if I would divide by 5 or by 22, because those numbers don't divide evenly. I'm going to take the GCF, which is 6. I'm going to divide top and bottom by 6. 6 goes in the top twice and into the bottom 3 times, and another equivalent fraction would be 2 over 3. Now notice that that equivalent fraction just happens to be a fraction that doesn't simplify anymore. I could not divide top and bottom by anything other than 1. So that's as small as the numerator and the denominator can be to be equivalent to that fraction. Now that leads me to this definition, what we call the simplest form of a fraction. The simplest form of a fraction is when the numerator and the denominator, remember the numerator's on top, the denominator's on the bottom, d for denominator, d for down, right? Or when the numerator and the denominator are relatively prime. I mentioned this just a little bit ago. Relatively prime means that their GCF is 1. Look at the 2/3. That's an example of a fraction that isn't considered in simplest form, because the GCF of 2 and 3 is 1. 1's the biggest number that divides into both evenly. So I have 4 examples here. I'm going to do very quickly here. I'm going to write in simplest form. I'm going to look at them. I'm going to see if something divides. I'm not going to be multiplying. I'm going to be dividing top and bottom by the GCF. Well, the GCF of 6 and 8 is 2. So I'll divide top and bottom by 2. I get 3 over 4. That's my simplest form. My GCF here of 25 and 40 is 5. Divide top and bottom by 5, I get 5 over 8. My GCF of the next one there, 27 over 42. For 27/42, my GCF is 3. 3 goes into both evenly, so 3 into the top 9 times, 3 in the bottom 14 times. And then 28 over 49, I'm looking for something that divides evenly into 28 and 49. I'm thinking 7. 7's my GCF. I divide the top by 7, it goes in 4 times. I divide the bottom by 7, it goes in 7 times. And those are considered simplest form. Sometimes they're called lowest terms for the fraction, but most of the time it's called simplest form of fraction. Now you can get good at these, and you can get good at finding your GCFs, but it does take a lot of practice, practice, practice.